Good afternoon, everyone. My name is Yupu Zhang, and today I'm going to talk about our work, ViewBox, integrating local file systems with cloud storage services. This is joint work with Chris Dragga and our advisors, Andrea and Remzi at Arpaci-Dusseau. So we'll know that the personal storage services are very popular, especially those cloud synchronization services like Dropbox, Google Drive, or SkyDrive. So these services are popular because they can provide a reliable backup on the cloud, and they can automatically synchronize your files across your devices. So it gives you a sense that we have like many copies of data everywhere. My data must be safe. But really? So we find these three problems. First, data corruption. Suppose you have a local file, say you have an image on your local machine, but unfortunately it's corrupted. So it's possible that the synchronization client would upload this file to a cloud and then push this copy to all your other devices. So in the end, you have many copies of bad data. And similarly, there is this problem of crash inconsistency. So if a crash occurs, it can leave your files, your data inconsistent on local disk. So similar to the corruption problem, the inconsistency could also be propagated. And we have also found this out of sync problem. As you can see in the figure, originally there is a file synchronized across all the devices. But a crash occurs while the user is updating this file to a new version. And after reboot, the synchronization servers could not detect such changes, so that this file is now out of sync. And then there is the third problem called causal inconsistency. It occurs because the synchronization services usually upload files out of order, such that the cloud state does not match a valid file system state. So here's an example. Suppose you're using a photo editing software, which keeps an actual image, file, and a thumbnail. Let's say the application modifies this file. So it will first write the actual image, the updated image to disk, and then generate a new thumbnail. However, because the synchronization client could not see this order, so it's possible that the client would first upload the thumbnail to the cloud, and then the cloud pushes the thumbnail to a tablet in this figure. However, now, unfortunately, a crash occurs. The other user using a tablet sees the updated thumbnail, who might think that the updated image has been synchronized. Unfortunately, this is not the case. So we think that many copies do not always make your data safe. The reason is that, first, on a local file system, the file system is usually the weakest link, because most systems, they don't check some data. So the corruption and inconsistency might be propagated. Therefore, the file system state is not equal to a correct state. This is incorrect. Then the second reason is that we believe ad hoc synchronization is harmful, because the synchronization client sees what other regular application sees, but it's not what the file system sees. As a result, the cloud state might not be equal to the file system state. So ideally, what we really want is this equation. So the cloud state, the file system state, they are both correct. Therefore, we are wondering what can we do to achieve this with existing systems. So here's our solution called ViewBox, in which we integrate a local file system with cloud storage services. What we did is, first, we enhanced local file system to provide data checksum so that it can detect problems. And then, with this cloud data recovery, we can utilize the redundant copies on cloud to fix your local failures. Therefore, ViewBox is able to ensure that the file system state is always equal to the correct state. And then the key part of this ViewBox is view-based synchronization. So here a view is an in-memory snapshot of valid file system state. So in ViewBox, it actually presents the file system view to the synchronization client, such that the client sees what the file system sees. So they have the same view. This would ensure that the cloud state would equal to a valid file system state. So here's the results. We built a prototype ViewBox around the ext4 and two services. We enhance local file system with data checksum, and we make ViewBox work with unmodified Dropbox and modified C file, which is an open source synchronization services. And both services can provide different level of consistency. And we have experiments showing that ViewBox is able to provide better reliability, such that there is no global data corruption, and it can automatically recover local failures using cloud data. And performance-wise, we find that ViewBox only incurs minimal overhead. For most workloads, the overhead is only 5%. And in some cases, for some workloads, ViewBox can actually reduce the synchronization time by up to 30%. So here's the outline for today's talk. First, I'll talk more in detail about these three problems, about how we use experiment to show the problems. And then I'll talk about the design and implementation of ViewBox. After that, I'll present some evaluation results. And finally, I will conclude and take questions. So for these experiments, what we did is we performed the experiments on this traditional file system, ext4, and a more advanced file system, ZFS. And we'll be focusing on these three services, Dropbox, OnCloud, and the C-file. So first, let's take a look at the data corruption problem. So for this problem, what we did is we injected corruption to a synchronized file on disk. So this figure actually shows you a regular write, which the new data would go through the file system and then get to the disk. But in our experiment, we directly flip bits on the disk such that the file system is not aware of the change, so it's a corruption. Then we perform various workloads. For example, we would perform data writes, which would overwrite a data block that is not corrupted. Or we just make metadata changes, such as touch or change mod. And then we will see if this corruption is propagated to the cloud. So here's our result. We first run a set of experiments on top of ext4. As you can see in the table, for data writes, as expected, the corruption is actually propagated to the cloud. However, in other cases, where there is only metadata changes, the corruption is still propagated. This is not good. And we also run the same set of experiments on top of ZFS. So we know that ZFS provides better reliability. It checksums data. Therefore, whenever the corrupted block is accessed, the corruption is detected by the file system. However, even ZFS could not automatically use data on the cloud to perform recovery. So the lessons we learned from the problem is that the synchronization service fails because they rely on file-level monitoring services like iNotify, which doesn't know what exactly is changed in a file. So the services has to read the whole file from disk to figure out what is changed. Therefore, it could not tell between legitimate changes from corruption. And the file system fails because most popular file systems, they don't check some data like ext4, NTFS, or HFS+. Therefore, all the corruptions could be propagated to the cloud. And then let's take a look at the crash inconsistency problem. So for this problem, what we did is we initially have a file synchronized on your local machine and cloud. And then we update the file from version 0 to version 1. And during an update, we actually inject a crash such that it's possible the affected file would be a mixed version of version 0 and version 1 after the crash. And then we observe how the synchronization clients behave. So here's the results. We first run the experiment on top of ext4 with order generation mode, which only provide metadata generation. As you can see, all these services exhibit erratic behaviors. In some cases, they might upload local inconsistent version to the cloud. But in some other cases, there is this out of sync problem. So the files are now out of sync. And then we run the same set experiment on top of ext4 with data generating and ZFS. Because the local version is always consistent, all these services behave correctly. They always upload the local version to the cloud. But in some other cases, for example, in this case, on cloud, we'll actually download the cloud version to your local machine. It might be correct for crash consistency, but it might violate causal consistency, which I will talk about in the next couple of slides. So here's the lessons we learned from this problem. So first, a synchronous service fails because they always check file metadata by their own. And if there is a crash, the metadata might be inconsistent with the actual metadata on the file system, which would cause those irregular behavior of the services. And then the file system fails because most file systems just use metadata generating by default, which could provide a little bit better performance, but it fails to provide data consistency. And now let's take a look at the third problem, causal inconsistency. So for this problem, what we did is we write a series of files in a specific order enforced by fsync. So in this case, we write A, B, and C. And then we see if these files are synchronized to the cloud in the correct order. So here is the correct order, A, B, and C. However, when we run experiments on top of ZFS and ext4 across all the three services, there are always cases where such ordering could be violated. So here's an example. So in this case, file B might be uploaded to cloud first, and then C, and then A. As a result, even if the file system is able to detect corruption or inconsistency, it might not be able to directly use the data on cloud for recovery due to a violation of causal inconsistency. So this problem occurs because the synchronized services usually synchronize files out of order, either depending on file name or file sizes. And this is actually a generic problem for the local file system, because now there's no efficient way to provide a static and consistent image to the synchronized services. So in summary, we find that both the file system and the synchronized services, they are all responsible for these failures. And because many file systems lack strong reliability mechanisms, therefore the file system state might not be equal to the correct state. And the synchronized client does not see the same way as the file system sees their state. Therefore, the cloud state might not be equal to the file system state. So this is not good. And we also find that not all problems can be avoided by just switching to advanced file systems like ZFS. As you can see in this table, even ZFS could not provide causal consistency. And then all the file systems, they are not able to utilize the data on the cloud for local recovery. So to solve these problems, we propose ViewBox. So let me first give you an overview of ViewBox. It relies on three major components. First is a file system we call the ext4 checksum. Basically, we just add data checksum to ext4 such that it can detect corruption and inconsistency. And then we have a user-level daemon called ClearHelper, which can fetch correct data from cloud to fix your local failures. And finally, a key piece is called View Manager. It's a kernel module which would provide this view-based synchronization. So the key idea is that View Manager would present the file system view to the synchronized servers, such that it can provide consistency and correct recovery. So before I talk about the architecture of ViewBox, let me give you some background on Dropbox. So in this figure, on the right side is the cloud. You have your Dropbox folder on the server. And on your local machine, you have a file system running on top of the disk. And then the Dropbox client relies on iNotify to monitor changes in your local file system. So here's an example of how this works. Suppose this file was already synchronized, and the user decides to update this file. Then the synchronized client would see a notification saying, hey, file 1 was just modified. So the Dropbox client would read this file from a local file system and then upload it to the cloud. So the Dropbox server already provides this file level versioning. So now the latest version is a red version 1, is a red file 1. Note that in this case, all the other applications sees the same thing as the Dropbox client. They see the same file system state. But in ViewBox, so the first thing we add is that we replace the original file system with the ext4 checksum. This ext4 checksum is dedicated to store the entire synchronization folder. And then we added the View Manager, which actually inserted this file system view to the Dropbox client. As you can see in this case, the other applications still sees the original view from the file system, such that this file system view, this View Manager, would not affect the normal operation of other applications. But the client gets a private view from a file system. So here's an example of how ViewBox works. Suppose the user updates these two files, file 1 and file 2. And then when updates are done, the View Manager would take a snapshot of the file system to reflect the updates in file system view. And in this case, the Dropbox client is actually using iNotify to monitor changes in the view. So in order to trick Dropbox client upload these changes from this static view, View Manager would actually regenerate iNotify events. So here, file 1 is modified, and then file 2 is modified. So after the client sends both copies to the cloud, so now the cloud moves on to a new state. So with ViewBox, we are able to provide file system level snapshot on the cloud. And the cloud will store multiple snapshots, which can be used for recovery. Let's see what happens if we have a corrupted file. Let's say the file 2 is corrupted, and then the file system would be able to detect the corruption by using checksum. Then it will contact a cloud helper, which would bring the correct copy from the cloud and use that to fix the local corruption. So next, I'll talk about how we implement these 3 components. So for local detection, we use equal checksum. So the way we did this is that we added a fixed size checksum region in every block group in 84, such that every 32 bits in that checksum region is a CLC checksum, which maps to a data block in the block group. So we can use this checksum to detect corruption and inconsistency. So you will find more details in the paper. And then this cloud helper would actually is a user-level daemon, which talks to a local file system and communicates with the server side. So whenever a corruption is detected, the cloud helper would fetch the correct block from the cloud. And if there's a crash, it actually offers 2 types of recovery. You can either recover inconsistent files individually, or you can choose to roll back the entire file system to the latest synchronized view on the cloud. So next, I will talk about view-based synchronization in detail. So View Manager is the module responsible for this synchronization. It has to create file system views at the appropriate time and upload views to the cloud through the synchronizing client. There are actually 2 challenges in View Manager. The first one is, how can we provide consistency? Because the local file system still runs in order mode. So the technique we use is called cloud journaling. And then the second challenge is, how can we create views efficiently? Because the local file system does not support snapshot. So we use this incremental snapshotting to create views, create snapshots in memory. So let me first introduce this first technique, cloud journaling. The basic concept is to treat the cloud storage as an external journal. So View Manager would carefully track local changes from the file system and upload those changes to the cloud at file system epochs. And the View Manager would keep 3 types of views. First, there is a local active view, which represents the current file system date, and is also used to track changes in current file system. And then there is a frozen view, which is actually a in-memory snapshot, which represents the last file system state. And then on cloud, there are multiple synchronized views, which could be used for recovery. So here's an example of cloud journaling. Suppose originally we have this view number 4 synchronized on cloud. And now the current file system, the active view, is at view 5. So when there are updates to the file system would move on to this epoch 1. At this time, the View Manager would freeze this new view 5. And it will start uploading this view 5 to the cloud. At the same time, the file system still accepts new changes. So now the view 5 has been uploaded to the cloud completely. But we cannot freeze this active view 6 at this time, because we have to wait until our local file system reaches epoch point, and then freeze this new view in order to provide consistency. So if the machine crashes before this view 6 has been uploaded to the cloud, we can actually just roll back to this view 5 on cloud after reboot the machine. Note that in order to implement cloud journaling, it might require some server-side changes. So in a single client scenario where there is only one client synchronizing with the server, so there is usually just one direction synchronization from a client to the cloud, so there is no server-side changes necessary. So we implement this scenario with Dropbox because we have no control over the client or the server side of Dropbox. But in multi-client scenario, where there are multiple clients running our systems synchronizing data at the same time, we have to make sure that the server does not propagate a partially updated view. And on the other side, we have to make sure the client can handle conflicts nicely. Therefore, we implement this scenario with C file, which is open sourced. And now let's take a look at the second challenge, how to efficiently freeze a view. We have already seen that a frozen view is usually short-lived and kept in memory. So what we would like to see is that there is no changes to the file system on disk structure because we don't want to persistent that in-memory snapshot. And then we don't want the file system operations to be delayed. And finally, we want to minimize the memory overhead to store the snapshot. So the technique we use to solve this problem is called incremental snapshotting. The basic idea is to decouple the namespace and the actual data. So here's an example. So initially, we have this frozen view 4 in memory. It has already been synchronized to cloud. So now it's only maintained in memory and only the namespace is preserved. All data are still kept in the local file system. And then when there is updates in the file system, the active view uses these logs to track namespace changes and change the files. Both of the logs are stored in memory. And when the file system reaches epoch point, this epoch 1, the view manager would start to freeze this current active view file. What it does is it would apply the namespace changes to the previous frozen view, such that it can bring the namespace up to date to reflect the state of this active view file. And then it would actually mark all the changed file copy on write, such that it can leave all the file data in the active view in the local file system. At the same time, the active view starts immediately with a new set of logs, such that the ongoing file system operations would not be interrupted. And all those cloud data is copied over to the frozen view only when the data block is changed in the current active view. And then when View Manager actually uploads the frozen view file to the cloud, it would regenerate iNotify events based on these logs to trick the synchronization clients upload the changes from the static frozen view to the cloud. So next, I will present some evaluation results. So in the evaluation part, we want to answer these two questions. First is, can ViewBox offer integrity, consistency, and recoverability? And the second question we want to answer is that what's the overall overhead of ViewBox running user workloads? So here's a setup of our experiment. So first, I will show the reliability results. So for this experiment, we performed the same set experiment as we did in the motivation section. And as you can see in the table, ViewBox is able to detect and recover all local corruption. And if there is a crash, ViewBox would always download the consistent version from cloud. And we have also confirmed that the causal ordering is also preserved by ViewBox. And next, I will show some performance results. So first, we replay the trace iPhoto view from iBench, which emulates a user sequentially view reading 400 photos. It's read dominate. And this bar graph shows your runtime of this workload running on top of the unmodified ext4 and our ViewBox with Dropbox and C file. So the runtime is the time it takes to just finish the workload, but the synchronization could still be going on. As you can see in the figure, the runtime overhead is less than 5%, and we have also measured the memory overhead. It's generally less than 20 megabytes. Note that the workload actually contains more than 1 gigabyte of data. So the next graph shows you the synchronization time, which is defined as the time it takes to finish synchronization all updates generated by the workload. As you can see in the left two bars, there is actually a huge increase in the synchronization time with ViewBox and Dropbox. The reason is that because we don't have any control over the Dropbox, but we want to implement this file system level snapshot on the server. So we have to create a list of path name and version number of all the files and directories that belong to our view. So in order to get this information, we have to query the server at a directory basis. So this workload contains more than 1,000 directories. So whenever we upload a view, we have to do like more than 1,000 remote work, which would incur more than 1,000 round trip time. So this would contribute the huge overhead. With C file, we have control both the client and the server side, so that we can just use its internal metadata as our view metadata. And next, I'm showing you the performance of photo editing workload. In this workload, as you can see, Dropbox still incurs very high synchronization time. But with C file, there's actually a 30% reduction in the synchronization time. The reason is that the original C file would actually delay uploading if it finds that the current synchronization folder is being constantly modified. But with ViewBox, because we are able to present a static view to the synchronization client, such that the synchronization client could keep uploading data to the cloud without any delaying. So now I will conclude this talk. So we find that cloud storage service and the file systems actually fail to protect data because all these three states are not equal. And we propose this ViewBox solution with an enhanced local file system and view-based synchronization, such that we can make sure the cloud state is equal to the file system state, and both of them are correct. So finally, we're wondering what can we achieve with even tighter integration. For example, maybe we can achieve like better performance or better security or privacy. And thank you. I will now take questions.
Hi, my name is Arlen Kangarlu from NetApp. So my question is, when there's corruption, you fetch the correct version of the data from cloud. And what are the implications for how do you preserve causal consistency during recovery? Do you roll back causally related files to some previous version, to some previous epoch?
So your question is like, if there is a corruption, so do I like just roll back the corrupted file to a previous version?
Right, but there are also some causally related files. How do you treat those?
So, so if you really care about like the consistency of the whole file system, ideally you would want to roll back the whole file system.
Right.
But I think in most cases you can just roll back individual files, which would give you very good integrity and consistency.
And when you roll back individual files, that also has implications for running applications that are working on.
Can you repeat the question again?
So what are the implications of the rollback for an application that is operating on that file? Would it be handled nicely, or would it cause any problems for the application?
Well, I think the application has to be aware of this kind of
would it be handled nicely, or would it cause any problems for that?
An application that was writing into the middle of a file and it could crash and be inconsistent, that's cheating because that application isn't already consistent. What if you had a properly behaved application that would, for example, write a new copy of the file with a tilde on the end and atomically rename it over the original file? Does that still have problems?
I'm sorry, can you repeat the example?
So you had an example where you had an application that was writing to the middle of the file and it crashed and there was bad data that got synchronized. But I claim that application is wrong. That would not have survived even without Dropbox. It would still have been inconsistent. A proper application will do something like make a new copy of the new version of the file next to the original copy and then atomically rename it over the original copy. Does that have problems with Dropbox?
In that case, if there is a crash, and if the local file system is able to like either keep the old version or a new version, there will be no problem with Dropbox. But in your case, there could be still like this causal inconsistency with Dropbox against other files.
Totally.
All right, let's thank Yupu.
Thank you.